Okay, so please.
Great. So thank you very much for the introduction. First of all, thank you for the kind words. Also, the kind words about the geopark. And this is very important. The IGEN geopark is very important. And I have started my work in Indonesia at MERAPI. And I think there's some similarities. As you mentioned, there is carbonate basement, and that's beneath MERAPI as well as beneath IGEN. And so I think some of the lessons we have learned from MERAPI can be transferred. Although MERAPI is highly active, it's a very dangerous volcano. I think IGEN is more friendly, but we can kind of learn these lessons, hopefully. So I will give a presentation now. It's going to be a regular kind of 45-minute approximately presentation. And some of the data I show are very scientific. For those of you who are not quite familiar with some of the geochemistry, feel free to ask me later. But for those who are interested, I will go a little deeper at times. So hopefully we will find a good compromise for the different members of the audience here. So first of all, we all know that volcanoes are fed from depth. We only see the cone at the surface, but usually there's a huge system underneath, a plumbing system as we call it. And magma is a probe into the interior of the Earth. So the magma that erupts as lava or as ash is something that helps us to understand what's going on under the volcano, about the source regions, about the conditions of magma ascent, and of course also about the rocks the magma has passed. For that, we need to learn to understand how to read magmatic rocks. And magmatic rocks usually have a silica content of about 45 to 75 weight%, and they usually fractionate due to crystallization. So this goes back to Mr. Bowen's work in the 1920s. It's 100 years old, this concept. And if we have magma and it cools, then we start to make crystals. Olivine first, and then pyroxene and plagioclase. And later we have other minerals like hornblende and biotite. And eventually we make quartz in the very high silica system. And the idea is that we take these minerals away. And by doing so, we actually increase the silica content of the magma. So this is called fractional crystallization. And this is one of the main reasons, or at least it was believed for a long time to be one of the main reasons for why magmatic compositions differ amongst different volcanoes. However, having said this, part of the problem is that if we use Bowen's scheme, it's like a distillation process. We use a lot of basalt to make very little highly evolved rhyolite, as we call it. And this should give a scheme like shown here on the left hand. But in reality, it's often very different. And in Indonesia, what we find is we have a lot more andesite and a lot more rhyolite and far less basalt than Bowen's scheme suggests. So there is something not quite right with this theory. And my hypothesis is that the crust, the thick crust under Indonesia is playing a considerable role. And this is what I'd like to discuss today. So, and this is not just the case in Indonesia. We also see this in continental systems like New Zealand. New Zealand is a bit of broken off continent from Australia, and there it's even worse. But of course, our focus is on Indonesia, but I want to show that Bowen's scheme is not universally applicable. And the more continent you have, the stronger the mismatch to Bowen's scheme as we observe it. So other processes must take place. And this brings us into the subduction zone. So here we know that in the Indonesian case, we have the oceanic plates subducting under Java, for example, and at about 6 centimeters a year. And the subduction produces fluids, and the fluids, they are believed to change the conditions in the mantle wedge, causing melting there. We know that this produces basaltic magma, but as I said, in many parts of Indonesia, we have evolved volcanism, andesites, dacites, rhyolites, And the big question is, what happens in between? What happens between making the magma and erupting it at the surface? And often this yields explosive volcanism. And I think partly the answer why we have explosive volcanism in Indonesia is also contained in the crust and not only in the subduction zone. So I want to evaluate these processes, and eventually, hopefully, we can contribute some concepts, some thoughts about how to provide some tools for hazard assessment. And here I'd like to give you a little background on MERAPI, because I've been working there for over 20 years, and I'm slowly also working on some of the other volcanoes. And I will give you some petrology and mineralogy. Then we'll talk about calc-silicate inclusions or skarn type inclusions. And then we talk about some geochemistry, and then I will summarize some of the ideas that I have presented. And then, of course, I would be very happy to discuss and try to answer your questions if there is any. So Indonesia has a lot of active volcanoes, and the number changes all the time, I think. But last time I looked, it's at least 129 active volcanoes, and MERAPI is here in central Java. And the subduction of the Indian Ocean plate is at about 6 to 7 centimeters a year. And all the yellow dots here are active volcanoes. And here, of course, Ijen is also there in East Java, but MERAPI is in central Java. And there are small differences between there, but in broad scales, there's also a lot of similarities. Let me give you a quick background to MERAPI. It's one of the most active and most explosive volcanoes on the planet, and certainly also in Indonesia. It was a decade volcano in the International Decade of Disaster Assessment, and it's characterized by these longer periods of dome growth. They happen on years to tens of years basis, and then there's also short periods of very explosive events, blasts and flows, and not always do we get good signals that we can monitor. And some of these explosions, they come out of almost nowhere. And this is a huge challenge for the people living on the volcano, because sometimes the volcano warns us with tremors and earthquakes, and sometimes it does not. And we have quite a number of casualties as a result of that, and many people live close to the volcano because there is a good agriculture. There's a lot of sand mining as well. It's very kind of nice. The climate is very nice if you live a little bit higher in altitude. So many people live around the volcano. And there was this rather unpleasant event in 1994 where 63 people died at a wedding, which was outside the exclusion zone, outside the forbidden zone. And this tells us that we don't fully understand the volcano in all its details yet. So this makes predictions very, very difficult. And many of the monitoring teams talk about the source mechanism problem. So, and I started to work some 15 to 20 years ago. And one of the big events back then when I was a young researcher there was what happened in 2006. Well, there was an eruption in 2006. It commenced in March with increased seismicity. And then we had pyroclastic flows starting in May of that year, and they peaked in mid-June. There was a big earthquake end of May, and after the earthquake, the activity of the volcano increased dramatically. And strangely, this earthquake happened about a month after the volcano woke up. And I believe that the crust plays a role here. The crust has faults, and it has a lot of fertile rock, meaning rock with a lot of gas. And I think there's a connection, and I'll try to talk a little bit more about this. But there was a big earthquake on the Opak River fault, and unfortunately, many people were affected by this earthquake. But from a volcanological point of view, after the earthquake, the volcano got more active for several weeks, and there was more rock falls, there was more kind of activity. And this is very, very important, that the interplay between volcano and crust is probably something we need to think about. So the earthquake of 2006, the big earthquake on the 26th of May was a 6.4, and it resulted in over 6,000 fatalities and 1 million people that were homeless. And it happened on the Opak River fault. And I believe that there's a connection between MERAPI volcano and the Opak River fault. And I did some calculations, and if we produce a lot of CO2 from the volcano, but also from limestone, we could have this travel in subterranean pathways. And it would take about 1 month from the volcano to the Opak River fault. And this is exactly the time between the volcano erupted and the big earthquake. So I hypothesized before that there is a connection between the limestone under the volcano and the hazard aspects on the surface. And I'd like to research this in a bit more detail now. But here's some impressions. This is some pictures of the damage caused after the 2006 earthquake in Jogja. And here you see many of the houses were destroyed. This is the university in Jogja. And well, there was severe damage. Many people were affected, and many houses were destroyed. Many people were homeless for many weeks and months afterwards. And here there was schooling, which was very improvised. I think it was heroic to see how the people coped with things, but of course it was also heartbreaking to see the damage that was caused. So I think we need to understand the volcanoes, and there was the big pyroclastic flow of June 14th, which affected this village here, Kali Atem village, which was very close to the volcano, and it got in part buried. The village was evacuated, thankfully, but 2 volcanologists were in an observation station, and unfortunately, these 2 volcanologists, they died in the eruption. So here's the observation bunker in the lower image here, and this is where the observation people were stationed. And when you look at the deposits at the time, you will find that there's a lot of these inclusions here. And this is a foreign inclusion inside the lavas or the pyroclastic deposits of 2006. And this intrigued me greatly. And I thought there is a connection between these inclusions and the violence of the eruption. So, and this got me interested in various inclusions, and I started to look at some of the larger blocks in the pyroclastic flow, and what we saw there was these Schlieren textures, or these kind of stripes here, and you see them here. And after a while, I worked out this is a form of magma mixing, but what we also found was these kind of foreign inclusions, and they are calcsilicates or skarn type inclusions. Skarn is actually a Swedish word, believe it or not. It was first described here in Sweden as a contact metamorphic problem between magma and limestone. And this is where magma interacts with limestone. And this is what we see. And there's actually quite a lot of them inside the deposits if you look carefully. And often they are sown. Here you see one with green margins and a white interior. The white mineral is wollastonite, a calcsilicate mineral, and the green one is diopside, which is also a pyroxene, but it's slightly different in composition. I'll talk a little bit more about those later in the talk, but we also found a lot of other inclusions, and I want to go and look at these first before we go back to the calcsilicates. So what we found was not just the andesite that erupted, we also found basalt inclusions, and here's one, and this is believed to be a liquid basalt in an andesite. Then we found plutonic inclusions. Here's a diorite inclusion inside the andesite from MERAPI. We found megacrysts of amphibole in this case. They can be several centimeters large, so quite striking. And we found partly resorbed, partly eaten up microgabbros, and this also shows that the magma is interacting with the crust. And of course, as I said, we found these calcsilicates, and here's a very nice one encased in the andesite lava. And of course, there's a lot of crystals in the MERAPI andesite, and the crystals, they often are zoned, and they tell us something as well. So I will talk a little bit about crystals later on too. Now, putting all this together, this is from my teaching. This is kind of how we picture magma reservoirs, and the upper image is a model from the MERAPI Volcano Observatory. So somewhere inside the crust, we believe there's a magma system that feeds the volcano, and all of these processes happen there. We have plutonic rocks that are forming, we have assimilation, we have all these things, but my sketch is very general and it doesn't tell us a lot about the details of this. And it also doesn't really tell us where exactly these processes are happening. And this is work that was done by Ratamopurbo et al. And they determined an aseismic gap, and that is here, in a study that was published in 2000, and the data come from the year 1998. And they believe this is the magma chamber under MERAPI, but a later study in 2003 couldn't find this anymore. So the question is, of course, was it ever there? Did it freeze over? We really have a poor understanding only, and this leads us to study the volcano in more detail. So when we did look at these plutonic inclusions, I had a PhD student there, Chadwick, and many years ago, and she did the first barometry, and several other people did barometry on minerals afterwards. And what we found is that the amphiboles seem to come from very, very deep, and the latest paper there is Peters et al. 2017. The pyroxenes are deep and shallow, and the latest paper there is Deegan et al. 2016, and various other papers that are out there. And this kind of tells us that there is separate storage regions. It's not just one magma chamber under MERAPI, it's likely several magma chambers. And I started off with this kind of concept many years ago, about 10 years ago. And there we believed that the mafic rocks, the gabbros, come from very deep, the basalts come from the upper mantle or the lower crust, and the diorites come from within the crust. This picture has been refined over the last few years. It got clearer and clearer that even that was simplified. And what we learned is that there is at least 3 different reservoirs. There is a deep reservoir, there is a mid-crustal reservoir, and there is short-lived shallow reservoirs as well. So, and to fit this into the seismic tomography from the region, this is the seismic tomography published by Wagner et al. There we can try to put this together. Here's a sketch of the seismic tomography from the MERAMEX project. This was an Indonesian-German collaboration project. And the red area is where melt is present, but the seismic tomography cannot resolve the details very well. So the barometry data were plotted on top of it. And laterally, our barometry is not very good in terms of saying exactly where this happens, but vertically it's very good. So we know that the barometry data match the anomaly. So that's a very comforting result. So we have a good idea that indeed this red area is where the magmas are stored. This is what the data from the mineralogy support. So we have a multi-system here, we believe, and over the last few years, things got more and more detailed. And in various papers like Deegan et al. And also Geiger et al., there is now increasing evidence for multi-tiered, multi-level storage systems with very shallow ones. We call them sharks, shallow arc storage magmas. They are often residing in the uppermost crust. And for MERAPI, on the right-hand side, we can now say that there's a mid-crustal storage region, a deep crustal or upper mantle storage region, and there is a shark system, a shallow arc magma storage system under the volcano. And this is recorded in minerals as well as in inclusions. And this is where magma gets in contact with sediment, with crustal carbonates, and this is where this magma crust interaction happens. Now, if this is true, we should see this in the feldspar crystals, because andesite from MERAPI has many, many feldspar crystals. And here we looked at feldspar zoning. We like to think that we can read this like tree rings, and the high AN value, the high calcium value, this would be a more silica poor magma, and the low calcium, the low AN value, would be a silica rich magma. If we look at these crystals, it actually goes up and down. It starts with low values, then there's big rims of high values, then it goes down again and up again. And this looks very complicated. So we looked at more of the crystals, and all of the crystals are very complicated. And we find them sometimes rising towards the rim, sometimes going lower towards the rim in calcium value. And well, how can we explain this? A traditional kind of magmatic approach would be that we are jumping around on this phase diagram between basalt and andesite, between AN 90 and AN 50. How can we visualize this idea? Well, here's a little sketch I made. If we have a deep system with high calcium, high AN crystals, and a shallow medium crust system with AN 50, for example, and we bring magma from the deeper part to the shallower part, we can overgrow them in different ways. So here we would then produce some crystals that have high AN and some crystals that have low AN rims around different cores. This was our working hypothesis, and if this is true, then this should be consistent also with the isotopes. And what we did then is we used this new and emerging technique. This came up about 15 years ago, and what we did there is we drilled the crystals. Now I'll take a deep breath, because it's basically a microscope with a drill from the dentist. It's like a dentist drill, and you can drill individual parts of a crystal, and you can sample it, and you can analyze this. So this is what we did, and we have one of these instruments here in Uppsala, and we're using these very fine dental drill bits, and we can resolve very small areas. There's a computer support system, so we can define, for example, here the core, we can define a rim, and we can drill that out. And we analyze this. This was published as part of the PhD thesis of Jane Chadwick already some 13, 14 years ago. And we looked at the crystals, and we looked at their isotope record, in particular the strontium isotopes. And if you're not familiar with this, limestone has very high strontium isotopes, and magma usually very low strontium isotope values. And what we found is that there was no systematic relationship here. This turned out to be very, very complicated. And we found that the high calcium areas in the crystals sometimes have very high strontium isotopes, completely opposite to what we would have expected. This got us thinking that, oh dear, maybe we need a source of high calcium and high strontium. And this, of course, could be the limestone in the crust. And this is what we explored further. Here's another example. Again, the high AN areas here in some zones, they are coupled with the highest strontium values. And this is very difficult to explain with a purely magmatic system. And here's another example where we have a core in a crystal with high AN and also very high strontium. I should say that the width of these bars, that's the error of the analysis, that's the uncertainty. So these are very, very high quality data, and they show that there is a lot of complications. There must be crystal that come from the limestone or from skarn, and there must also be magma that got interacting with limestone. So these data showed us that there is a whole new world of processes that we don't fully understand. this was really the start of the kind of concept of magma-carbonate interaction at MERAPI. We thought at least, but later discovered that there was some earlier work that had thought about it as well. And I'll say this later, but in terms of modern geochemistry, this was really the start. And here, what we see is that there is mismatches between the different parameters. And when we look at a strontium diagram, the recent MERAPI hole rocks, they are very different to the feldspars, and the ground mass is also elevated. And this should not really happen in an entirely magmatic system, but it can happen if we have interaction with sediment, which has high strontium and high calcium. So we started to look for these kind of inclusions, these calc-silicate xenolith, and they form from reaction with limestone. It's a contact metamorphic or pyrometamorphic system. And the Swedish word skarn is here again. So they are skarn type. And we often find that there's bubbly textures at the interaction. And I'll come back to this later. We believe that there's a lot of gas that comes from the limestone. And some of the most gas-rich volcanoes happen to be on sedimentary crust. And I think there is a connection between them, which may also be relevant for IGEN, by the way. So we looked at this in detail, and this is a limestone quarry near MERAPI. And when we look at some of these in thin section under the microscope, we see that there is a gradation, and we see that in the underside here, we can have some of the plagioclase coming from these inclusions, and they're getting detached. So the idea that we have crystals, foreign crystals, coming from the calc-silicate inclusion seems very real. We also see that they are zoned, and what we see here is that we get increasing wollastonite the further in we go with these inclusions, and we also have a change in diopside and in particular in anorthite, the calcium component of feldspar. So indeed, there is clear evidence that there is interaction between the magma and these country rocks, and there has been a conversion of the limestone to these skarns. And I bring you back to this diagram here. If we put the calc-silicate xenolith, the foreign inclusions, and the local crust on this diagram, they plot at very high strontium isotopes, and therefore they can explain these variations that we saw earlier. So this made us think that we need to kind of work more on these inclusions. And when we look at the feldspars, the feldspar composition in MERAPI, we measured almost 2,000 crystals here. And we also measured about 150 in the calc-silicate inclusions. And indeed, we see that there's an overlap here. This is very important because it means that many crystals in MERAPI andesite can actually come from these foreign inclusions from the crust. And if we look at this histogram, we have two peaks here. It's a bimodal system with a high AN and the medium AN. And this is what crystallizes in the magma itself. But some of the high AN could come from the crust because that's what we find inside these inclusions. So when we look at the strontium isotopes overall, many of the deep plutonic inclusions, they don't show a high strontium because they are formed very deep. They are formed below the sediments, but many of the lavas in turn, and of course the calc-silicate rocks and many of the late-grown feldspars, because feldspar grows rather shallow in the system. It grows only in the top 20 kilometers of the crust. There we see that the influence gets stronger. So deep in the magmatic system, there is of course there's no carbonate influence, but shallow in the system, there's a lot of this. And we thought, okay, strontium is a good parameter, but we want to test it further. So we looked also at oxygen isotopes, and oxygen isotopes is a major element because most silicate rocks consist of up to 50% oxygen. And what we see here is that the deep crystals like pyroxenes, they are not very high in oxygen. Morp is the magmatic value here. This would be the magmatic reference, and these pyroxene crystals, they are mainly magmatic, but the higher up we go, the lavas increase, and then the calcsilicates and the local crust, they have very high values. So there's an overall increase here. And this lower one, this diagram is not yet published. It's going to come out in spring next year. There's a book coming on MERAPI, and I am one of the editors, and this is from one of the chapters in the book from Deegan et al. 2022. And there is even more of those data. And you see that there's an increase with elevation. The higher the magma rises in the MERAPI system, the more limestone interaction seems to take place. So this is work I did already in 2013. And this is also oxygen isotopes. And if we take a mantle magma and we let it fractionate this way, irrespective of which fractionation calculation you do, whether it follows this one or this one, what we see is that at some point, the magmas of MERAPI take off there. And if you look at the different xenolith and volcanogenic clasts and limestone, we see that many of these samples seem to move towards the calcsilicate inclusions, which are given here in blue. So here we get strong evidence, and we did this here for a different suite. We get strong evidence that there is interaction between magma and these limestones of the upper crust. So this brings me on to the PhD study of Jean Whitley, who graduated last year from Kiel University, and I was marginally involved, and his supervisor, Ralf Gertiser, he and Ralf Halama, he had two supervisors there. They got him to work on many of these calcsilicate inclusions in more detail. So I'm going to spend a few minutes on this now. So here's some examples. And as I said, they are made of wollastonite and diopside, but also a lot of really complicated skarn type minerals. And here is some examples of them. Often they have vesicular textures here. Often we get bubbly areas whenever magma and carbonate interacts. It's a bit like hydrochloric acid on carbonate. It starts to fizz up. And this, of course, is what's happening under a volcano then, because magma is rather kind of acidic compared to limestone, and they interact in a usually quite volatile way. So here's a close-up of this. It's a very complicated situation. Often we see these fragments breaking up, and very often we see these little bubbles here in the contact zone. And this means that CO2 comes also from the limestone, not just from the volcano and from the magma itself. So I showed this diagram before. This is just for impressions. We don't have to go and do it again. But there's very complicated interaction textures and very complicated mineralogy. This is from Whitley's PhD thesis, and he identified the zones in them very carefully. And I don't want to go into details, but he found that there is different minerals and different gradations, including garnet and magnetite, and different zones of glass as well. And this he believed to be an interaction. So studying this further, and this is partly work by Whitley and partly work by Francis Deegan, there we see in these little element maps from this contact zone between a xenolith and the magma that there is a mobility, that calcium seems to migrate from the inclusion into the magma, while magnesium seems to migrate from the magma into the inclusion. And that means it's an interaction. It's not a one-way process. And Francis Deegan, and in particular Jean Whitley as well, they found some remnants of calcite in some of the inclusions. And here's some remnants of calcite. And here is also a remnant of calcite. This is a very zoomed in view of one of the inclusions. And this is what Jean Whitley investigated for his PhD. And he kind of used different methods. And he first of all used thermometry. He worked out the temperatures for these things. And he found that the interaction must have happened at very high temperatures. In these areas here in the glass, he determined temperatures of 800 degrees. And in some of the minerals, he determined, in some of the inclusions, he determined temperatures of up to 900 degrees. So this is a magmatic interaction. And he puts this into the shallow system here. So here we have the melt inclusion data, 900 degrees, here 800 degrees for the glass. And he argues this is where this happens in the very shallow system. And here's a sketch of how he wants this to happen. We have crustal carbonate limestone here. We have basalt magma here. And then we have an aureole of reaction, and then bits break off, and that's the xenolith we see. And this, of course, releases also CO2. So this is then work by Francis Deegan mainly on experiments, and this was published in various papers starting in 2010, but also 2016. And here we wanted to see how quick is this process? Is it a quick thing? Can it go fast? And I don't want to go into great detail, but we used this instrument here. This is a piston cylinder at the INGV in Rome, the National Institute for Geophysics and Volcanology. And what you do is you make a little capsule out of gold or platinum, and you put magma in there, and you put some carbonate in there, and we let this react. And first of all, what we see is we get loads of CO2 bubbles, and this was a very good result. So our reality check worked. What we see in the rock record is true. We see a lot of CO2. And we were shocked by how quick this is actually happening. So here's the results of an experiment, 1200 degrees temperature, 0.5 gigapascal. So this is in the upper part of the crust. And 0 seconds means we only heated up the experiments to target temperature. The heating up period was 6 minutes. And this is a 60 seconds experiment, meaning that it was held at target temperature at 1200 degrees for 1 minute. And you see, after 6 minutes, the carbonate starts to disintegrate and form these aureoles of contaminated magma. And after only 1 minute more, the flakes of carbonate almost completely gone. They're digested by the magma, and we get many, many bubbles. So here you see all these bubbles, and here's a tiny carbonate left after 60 seconds. And here, after only the heat up, we have a larger carbonate and this aureole of contamination. So this was quite astounding, because what it tells us is that the interaction is very, very rapid. It's super fast. And here's just a time series, 90 seconds after target temperature, 150 seconds, 300 seconds. And after just a few minutes, there's no carbonate left. Now, this is an experiment. Experiments are, of course, idealized. But what we see is that when we do analysis, we see along this line here that we see carbonate being assimilated into the magma, and we can determine that it was interacting with the magma in these experiments. And this helps us to understand nature a little better. So we then also used the micro drill again, the dental drill on the microscope I mentioned earlier, and we drilled out some areas. And indeed, what we found is that the natural data of basalts and feldspars here on the strontium diagram, they can be matched with the crustal xenolith and the local limestone, and our contaminated experimental glasses, they plot here, and the uncontaminated one plot here. So we had really good evidence that some of the strontium enrichment that we see in the crystals is indeed from the limestones. So we have experimental proof here, not just inference from the rock record. So, but let's talk a little bit more about the gas coming out of this, because this is the important thing. This is what triggers explosions. And here in nature, we see these bubble trails, and this area here is this area here. We see many different little bubbles where the magma intrudes them, and this is exactly what we see in experiment. So here you see these big bubbles, and you see a little intrusions of magma into the carbonate, and it was actually shocking that the textures are so similar between the rocks and our experiments. And here's a very simple equation. This is what the problem really is. If we have carbonate in the sub-basement of the volcano and we add magma with a lot of silica, we create a reaction. And this reaction makes wollastonite, which is calcium SiO3, and it liberates a lot of CO2. Limestone has 42% CO2. So this is a huge amount of CO2 that comes from the limestone potentially, and not just from the magma. So large amounts of CO2 could be liberated, and this is what we see in these bubbly textures. And of course, this can make overpressure inside the volcano and potentially lead to explosions. Now, is this reasonable? Well, we wanted to test this further, and now I'm going to show you a few more isotope plots to kind of really bring this home. This is the most recent work. And here we have strontium and whole rocks. Here we have carbon isotopes from gas collected on MERAPI. And this is where the gas plots relative to the whole rocks. And this is where normal mantle plots. And this is where the Javanese chalks are. And indeed, MERAPI gas is somewhere in between. So it has magmatic components, but it also has crustal components, and this is where MERAPI gas plots. So it's a mixture of volcanic gas and gas coming from the limestones. And here is just a plot. The local chalks and marine carbonates, they plot here. The fumarole gas from MERAPI plots here. And if you degas a rock, if the gas is all coming out of a rock, then the rock will change its isotope signature, and the andesites and calcsilicates plot here. And this is a bit complicated. This is going back to Holloway and Blank. This is when you degas something from fully charged with gas to all degassed. What happens is that the gas phase stays high up, the vapor phase, and the dissolved material in the melt or the solid goes down. So that means after degassing, the gas phase will be up here and the solid will be down here. So this is the solids and this is the gas phase. And indeed, that means that these calcsilicates have lost a lot of gas. And this is what Jean Whitley in his PhD looked at, and he exploited this. And this is a plot of oxygen isotopes versus carbon isotopes, and this is for different areas in the world that also have magma-carbonate interaction, like in Italy, Colli Albani and Vesuvius, but also Lascar here, and various other kind of settings. And you can either just degas the limestone, this is this trend, or you interact with the magma, and this is this trend here. And it's effectively this kind of trend, what we see. And indeed, for MERAPI, different samples here give us different trends. Some of them are just degassed. Some of them are interacting with the magma here and then degas. So the evidence was very strong. This was done by secondary ion mass spectrometry. The evidence is very strong that these calcilicate inclusions in MERAPI, they have lost gas and contributed gas to the volcanic system. So then we did some calculations, and if you think of a magma chamber with an aureole similar to the 2010 eruption at MERAPI, then the estimates would be between 9.5 multiplied with 10 to the power of 9 to about 1.8 multiplied with 10 to the power of 11 kilograms of CO2 that would be released. MERAPI currently degasses about 4.6 to 10 to the power of 5 kilograms of CO2 per day. And this is already a mixture between carbonate and magmatic gas. And in eruption situations, it could release a lot more. And we also did a calculation if we want to take a cylinder of about 1 kilometer radius under the volcano, the entire limestone under the volcano, then we get to this amount of gas that MERAPI volcano could release in its lifetime. Now, compared to anthropogenic CO2 emissions, this is still very small, but it shows that there's a lot of potential for uncontrolled explosions in these volcanic settings. So let's quickly finalize now with some gas work that we did. And this is the dome of MERAPI here. And you can go up there and there's fumarole activity. Here's just another impression of the summit dome of MERAPI. And I showed this diagram before. This is where the fumarole data come from. Here is CO2 that we measured, and it's elevated. So it's elevated from magma, from mantle towards these local chalks, towards the limestone. And what we did is we compiled temporal data and we sampled temporal data. And this is the mantle area, and we have some Krakatau baseline data. They're very mantly or magmatic. They're down here. But when we look at MERAPI, it's already elevated, and there's a baseline round about -4. But in 2006, together with the earthquakes, it jumped up towards marine carbonate. So I think that there's a connection between the MERAPI eruption of 2006 and the earthquakes and shaking up the system, creating a lot of interaction surfaces with the surrounding sediment and assimilating limestone that releases CO2. And a few years later, we sampled again, and this was another team that sampled the gray data. There, the anomaly was gone. So once the interaction, the reaction between magma and limestone had proceeded, then the system was calming down again. So during activity, during earthquakes and volcanic eruption, I predict that the interaction with limestone is particularly dangerous. And this is something that we often don't appreciate to this date. So there's this data spike in 2006. And if we do a calculation, this implies that at this point, most of the gas would actually have been from limestone. If this is the mantle, if this is marine carbonate, then about 70% of the gas, when we measured it in 2006, actually seems to have come from the crust, not from the magma. So just a very final word, helium isotopes. This is just another system. We don't have to go into details, but here we have measured helium isotopes, and if we kind of look at this, the crust has very low helium isotope ratios. Mantle MORP has very high helium isotope ratios. So here we have below 0.1, and this is round about 8 or 9 for MORP and a bit higher for ocean island basalts. And the values for MERAPI are about 5.5 to 7. So they're in between here. And this is MORP, this is crust, and this is where MERAPI falls. So helium is also indicating crustal influences. So just a final word to give you a scale of the problem. If we do a little calculation of a magma chamber that's maybe between 0.8 kilometer tall and about 1.2 kilometer wide, which is the seismic gap of Ratamapurbo I said earlier. And we have limestones packages well in excess of thicknesses of several kilometers, then the magma chamber can be entirely contained within limestone. If we take a cube, and I'm only taking 10% of the height of this reservoir, and we let this assimilate over 1 week, we would produce 60,000 tons of CO2 daily. And this contrasts to currently 700 tons on a quiet day at MERAPI. So this is hugely effective. And if you want to produce this amount of CO2 by basalt, you would have to take magma in a cube of 440 meters site length. So limestone can produce a lot more CO2 than fresh magma on a very quick basis, as the experiments have shown. So it's extremely effective. And it's therefore a serious alternative for explosive eruptions at some of the highly explosive volcanoes in certain parts of Indonesia. So let me summarize. We have a subduction system, and we make basalt in the subduction system. And there we're creating these basalts from slab hydration, dehydration, and hydration of the mantle wedge. And these basalts then, they do some crystallization, mainly of amphibole in the deep crust, and then they rise up into the mid to shallow crust, and they will fractionate pyroxene, but at some point they might get in contact with limestone. And of course, they will be replenished. So the more magma we put into these systems, the more reaction we get. And this can then actually lead to a lot of gas being liberated in the shallow crust just under the volcano, which can then lead to explosive eruptions that are not signaled by deep seismicity. So several of the MERAPI eruptions, but potentially also Kelut in 2014, didn't have a lot of seismic signals beforehand and only shallow seismic signals. So here I think the sediments in the crust could play a real role. And this is from the upcoming article in the Springer book by Deegan et al. And I'm a co-author there, so this is why it's okay for me to show. Here we're trying to put this into a system. And I think here the magma-carbonate aspect is very important. And this produces a lot of CO2 that is not often considered. Many volcanologists don't want to consider the crust. They like to keep their volcanoes uncontaminated. But I think this is something that is becoming increasingly recognized. More and more people seem to see this and understand this, that this is actually a problem of the magma interacting with the carbonate. So at some point in these multi-systems, in these multi-reservoir systems, we have magma rising up through several chambers, and they may just reach these shallow carbonates, and that's where an extra gas injection is provided, leading to very explosive eruptions. And sorry, let me go one back. Having said this, that this is becoming increasingly recognized. Here, I should point out that it was actually already seen by some of the very early geologists. Here's one of the Dutch geologists from almost 100 years ago. They found some of these limestone xenoliths, but it got forgotten. Here's the timeline from Scopus, from citations, and we did a search for carbonate assimilation and the limestone assimilation. And up to our work in about 2005 to 2007, there was very little citations referring to carbonate assimilation. But over the last 20 years, there has been an explosion in people referring to this, and I think this will rise further. So more and more people are recognizing this problem, and it's unfortunate because it makes our situation more complicated. It means we understand less about volcanoes, and it's not as clean cut as we like to think. So some people like to avoid it because it's a problem. Some people want to shut their eyes, but I think we need to seriously think about this because it's these events that we don't predict that are the most dangerous. So thank you for your time, and thank you for the attention. And I hope you found this a little useful.